Hello, welcome back. In this video, we'll discuss the X-ray diffraction. This method is widely used to characterize materials, especially to determine their crystalline structure. The crystal structure essentially corresponds to the determination of the lattice constants and crystal structure. The X-ray diffraction is one of the characterization techniques of the nanomaterials or nanoparticles or nanostructures. In this, we study the X-ray powder method. In our discussion, we'll be studying only the powder method, which is also called as Debye method. This method is called as powder method or Debye method. This method is used to determine the crystal structure. In this experiment, a monochromatic X-ray beam is used. When we say monochromatic, it means the beam of X-ray should have the same wavelength. Generally, the K-alpha radiation is used. Since this radiation is incident on a powder which is consisting of randomly oriented microcrystals, the randomly oriented microcrystals, they form the powder. So the powder specimen is generally placed at the center of the camera. What this camera? This camera is called as Debye camera. When we place the powder at the center of the Debye camera, due to the presence of various crystal planes in the randomly oriented microcrystals that are present in the powder, we are likely to get diffraction in different possible directions. The Debye camera will be in the form of a thin cylinder with two openings. One opening for the X-rays to enter, the other opening is for the X-rays to leave the camera. At the center of the camera, we will have the sample holder. Along the inner surface of the camera, we will insert a photographic film. When the X-rays are allowed to enter into the camera, these X-rays will undergo diffraction due to the various planes of the microcrystals that are present in the powder. A large portion of the incident X-rays, they would be leaving the camera from the exit. Here we have the exit. So on the film we'll have two holes. One hole corresponds to the beam entry, the other one corresponds to the beam exit. The powder sample generates the concentric cones of diffracted X-rays because of the random orientation of crystallites in the sample. As a result, we'll be getting several arcs on the photographic film. The powder specimen is taken in the glass tube or a quartz tube and it is kept at the center of the camera. Since large number of the crystals are randomly oriented in the powder, a set of planes which make an angle theta with the incident beam can have a number of possible orientations. Hence, the reflected radiation lies on the surface of a cone whose apex is at the center of the contact of the incident radiation with the specimen. All the crystal planes having spacing d reflect at the same Bragg's angle of reflection, that is theta. Let us consider n is equal to 1 in the Bragg's law. 2d sine theta is equal to n lambda, where d is the spacing between parallel planes in a crystal. Theta is the Bragg's angle, n is order of diffraction, lambda is the wavelength. So order of diffraction n can take values, n is equal to 1, 2, 3, so on and so forth. N is equal to 1 corresponds to the first order diffraction. We consider 1 as the value for the order of diffraction. So we'll be dealing only with the first order diffraction. If you look at the geometry, from the geometry we can write the full opening angle of the cone, that is 4 theta, and this can be measured by measuring the distance s between the two corresponding arcs on the photograph. So we can write 4 theta is equal to s upon r. 4 theta is equal to s by r into 180 by pi degrees. Here r is the radius of the camera. A list of theta values thus can be obtained from the measured values of S. Since the wavelength lambda is known to us, substituting the value of lambda gives a list of spacings of D. Each spacing is the distance between neighboring ＨKL planes. The HKL planes you will know from the Miller indices. From the ratio of the interplanar spacing, one can determine the type of the lattice. We shall now see how to calculate lattice constant. Suppose small a is the lattice constant and rho is the density of the crystal, then mass of the unit cell is rho a cube. And if n is the number of atoms or molecules in the unit cell, and capital M is the atomic weight or molecular weight of the crystal, and n is Avogadro number, then the mass of the unit cell is equal to small n capital M upon n. That is, rho a cube is equal to small n capital M upon capital N, or A is equal to n capital M upon capital N times rho whole power 1/3. With the knowledge of the lattice type, n can be calculated, and with the knowledge of the molecular weight M and the density of the crystal rho, the lattice constant A can be calculated. In this formula, small n is the number of atoms or molecules in the unit cell, and capital M is molecular weight or atomic weight, capital N is Avogadro number, and rho is the density of the crystal. In this video, we have stated that to characterize the nanoparticles or nanomaterials and the nanostructures, X-ray diffraction methods are used. Among the various available X-ray diffraction methods, the powder X-ray diffraction method is used. The powder method is also called as the Debye-Scherrer method, in which a camera is used. The camera is called as the Debye-Scherrer camera. The powder method is used to determine the crystal structure. In the powder X-ray diffraction method, a monochromatic X-ray beam is used. K-alpha radiation line is generally used for the X-rays. We take the powder of the sample. The microcrystals of the material are randomly oriented. The powder specimen is kept at the center of the camera, and we will have a film in the camera. We record the diffraction pattern originating from the X-ray diffraction on the film. Later we have seen the Bragg's law. We have said Bragg's law is 2d sin theta is equal to n lambda, where n is the order of diffraction, d is the spacing between parallel planes of the crystal, theta is the Bragg's angle, and lambda is the wavelength of the X-rays used. We have seen how one can obtain the theta angle from the camera. We have also seen how to obtain the lattice constant using the physical constants of the crystal, such as density, number of atoms, and the atomic and molecular weight of the atoms or molecules. We have seen that the lattice constant A can be obtained as A is equal to n capital M upon n rho whole power 1/3. Thank you.